Wow. Hey everyone. Hope we're doing well. Get the mic up here. Yeah. Apologies. Last week there was no time for anything. But we're back. We are going to continue 30 Days Lost in Space. Tonight we're going to get into day 21. And we're going to toy with yet another new component. So, without further ado, I'm going to dive in. Spirit levels high.
This
Nice.
close to liftoff, and you stepped out? Priorities, Explorer.
Come on!
But I blame myself.
The airlock was
you
left
need to
open.
see a lot more data at the same time than what 4 characters will allow,
No
and
kidding.
Darwin is not gonna fly. The problem is, again, power. If we shrunk LEDs down, they would use less and less power, meaning we could use more and more small LEDs. Good news, Explorer. The hero scientists have done just that. They placed a whole bunch of LEDs on the breadboard, threw it in a hot wash with their underwear. What do you know? They got an organic LED screen.
Nice.
And shredded their underwear.
Well then!
That's an issue for another mission. Today's task will involve having the screen display a simple message. Hello, world. An age-old greeting used by programmers across the galaxy.
I've used that
It's
forever.
not just a test. It's
Oh,
a
but it
symbol of
is.
the communication we're about to establish with our spacecraft
good
that will
text
ultimately be
description.
our ticket back home.
Okay.
Remember, while these may seem like simple tests, they hold vital importance for us.
I want to see how it
These
works.
checks and validations will form the basis of our ability to navigate our way back once we burst forth from this planet's atmosphere. So, Explorer, shall we dive into the wonderful world of user interfaces?
Sure.
Buckle up. It's going to be an enlightening ride.
I'm
All
using
right,
sketchy
Explorer,
shit.
let's start with
Doo-dah,
understanding
doo-dah.
our screen's display pins. Take a look. There are some pretty obscure TLAs here.
Oh, boy.
Here's what they mean. and
3-letter
do.
acronyms.
GND is ground.
Right.
VCC is power.
Okay.
Duh. SDA is serial data and
Right,
sends
and then
information or
the source
data
clock.
over the serial
Makes
line
sense.
using the I2C protocol. I do want to call out that a serial clock isn't something that wakes you up in the morning. It's a signal that keeps the data here from getting out of step or
I'm gonna pause here for a quick second. So my own 2 cents on the pin, serial clock and serial data. We've seen before on other components that have to synchronize with the internal clock of the Arduino. So for it to accept data through the serial connection, it needs to know the timing that the data is going to come down that pin. Without that, the data won't be legible, which is why we have yet another serial clock pin. It's kind of interesting to see that type of component in one of these displays. I've never actually worked with one of these displays, so to me, this is fascinating to see where we're going with this. But it makes sense that it would have those 2 pins. And then the other 2 are pretty straightforward, power and ground. I mean, you kind of need that, right? With LEDs, we've been getting our power directly from the Arduino and grounding out to the rails on the sides, right? Well, this is no different, except our data goes down a specified data pin to do the thing that we want. So, yeah. All right, we're gonna keep going.
out of sync, like traffic lights at an intersection or drummers at band practice, usually, if they're good. I mean, some of them just sound like you've dropped a bag of marbles on a water cooler.
Oh,
You're not a drummer, are you?
no.
Now let's talk about protocols.
Okay.
In the world of electronic devices, a protocol is a set of rules or procedures for transmitting data between devices. Think of it like a common language that allows devices to understand each other.
Okay.
Two common protocols are I2C, which stands for Inter-Integrated Circuit, and SPI, which stands for Serial Peripheral Interface.
Okay.
Both are used for communication between devices, but they do have their differences. I2C, like our display, uses just two wires, one carrying a sync signal, the other carrying the data.
Right, that makes
Great
sense.
system for simple components to talk to each other. SPI uses 4 wires, and we're not using it, so take a hike. No, it's important, but right now, I2C will do just nicely. Our screen uses
Okay.
the I2C protocol. Simple and versatile. A multi-tool protocol.
All right.
All right, Explorer, let's get our hands on the necessary library and put our OLED display through its paces. First things first, head over to inventor.io/libraries and download the U8G2LIB library. This library is going to be our faithful ally when dealing with our OLED display. Once downloaded, let's get it installed into our IDE. Here's how to do that. Click on Sketch in the menu. Then, click Include Library. Next, click Add Zip Library. Then, simply locate and select the downloaded file, which should be this one. Terrific! Now our library is all set up and ready.
Yeah, we've
to
done
go.
this before.
Now that we have our library installed, it's time for a quick test to ensure our OLED display survived the crash unscathed. What better way to do this than the classic "Hello World" check? Thankfully, our new library makes this easy with a handy function called drawstring, which looks like this. A string is a collection of letters and numbers like a word, sentence, or even this train wreck of a term. Seriously, that might be my new password.
Oh,
This
gosh.
function will let us display the phrase "Hello World" or any other string for that matter on our OLED screen. A successful display of this message will confirm that our OLED is in working condition and is ready
an
to
OLED.
navigate
All right.
us back home. And with that, it looks like you're ready for the next phase
I
of
technically
today's
said
mission.
analog display in
We'll
the
turn to
description, but it's an
instructional
OLED.
material that
Fair
I've
enough.
gathered, cached on the computer. It is also readily available in your mission resources. I know.
Or
know
in the
I'm
Go
the
Live.
best.
It's a lie.
Hello, everybody, and welcome back to day 21 of the 30 days.
Hello and goodbye. Put our music back on. Alright, cool story. Alright, so we're gonna hook up our power. Right, we're still using analog pins. So I'm not technically incorrect in saying that it's an analog display because it's not using the digital hookups, but I think I almost confused myself with the way I worded that, because when I think of an analog display, I think of something like a CRT. That's not accurate. That's not what this is. You'll get to see the component, and it's a nice little flat little display when I get that out here to hook it up. But yeah, this looks like a very simple setup. You need 2 analog pins to tie into the data stream and the source clock. So okay. All right, let me switch scenes. And we are going to start hooking our stuff up. Looks like we're going to use... The source clock is going to go into the last pin, 5, and then the data is going to go down 4. So that should be fine. Okay. Huzzah. All right, let me adjust the camera so that we can see what we're doing here. Because right now it's zoomed in a little too far. Or maybe not. I don't know. Let me get the stuff over here. I'm gonna have to do a teensy bit of cleanup here from last time. Because this is where we left what we were up to. So let me get these disconnected because we're starting with some new stuff. Because yeah, the last time we were doing this, we were working with this display. It only has the 4 digits and the colon in the center that we could toggle on or off. Now it has to be both dots, not just one with this particular board. There's others that have the capability to control individual dots. This is not one of them, which is fine. That's not bothering anything. It's just a distinction. Not a problem. All right, so we'll put those over there. And then that's more the male to female. We're gonna save our LED for another rainy day. And our buzzer. Wow. It's surprising to see how far we've come along. We've tied an awful lot of stuff in. Yeah. And there's absolutely nothing wrong with starting fresh once again. So we've got our board, we've got a red board, and then let me zoom us out so we can see. That's better. Right, because I want you to see this, and then I'll zoom in to show you where the wires are tied in and everything. So first things first, let's grab that little display and get that out of its little baggie. Okay. Alright. So here it is. It's got the display on that side, and then our 4 pins here on the back. So conveniently, I'm just gonna plug these directly into our board here, and then just attach the wires directly from here to here. If we had a bunch of other stuff going on here, which would have made not enough room for me to just pop this in, we absolutely could have just used the same trick that we did for a lot of other components and just use the female to male jumpers, but we don't need to. We could just pop this right in. So we're gonna pop this in the very first row. So we're gonna be plugged into pins 1 through 4 across the top. And then we're going to start wiring. So we know that we need to have voltage hooked up here, which is going to be, technically I'm looking at this upside down, so that's ground, that's VCC, so then that's going to be our voltage. And then our ground we'll do to the grounding pin. Now, I'm not plugging these directly into the board for the power. I'm plugging them into here, and then I'll jump from here to where we need to go over here for power. Only because I would very much imagine we're going to end up doing more with this for the next exercise. And they started like this, so we're just going to continue on like this. Okay, and then we need to hook up our 2 data lines, which we will directly connect to our board. So we're going to use orange one, and we'll use a brown one. No particular color, they're all just jumpers, just something for my own sanity's sake. Okay, so we need to plug the source clock, which in this example was the green wire, into the very bottom. So source clock is 3rd in line into 5th position on the analog side. So we haven't been using this side of the board all that much, but for this particular toy we will. And then same thing for the I forget what the acronym is for this piece. This is the SDA, or the serial line, which will then be plugged into the 4th port. So, without further ado, we now have, oh, almost there, 2 more we gotta hook up. We gotta hook up our 5 volts in ground. So, 5 volts, which is gonna be here, so that's VIN ground. Hang on, I gotta move this a little closer to my face. VIN ground 5 volts. Yeah, there we go. Tiny things, hard to see. Okay, got that there, and then this is our 5 volts, which we'll plug into the 5 volt rail, and then hook up our ground to our grounding rail. And then that just makes things a little easier on us, because if for some reason we do need to disconnect this, it's just the 2 power lines here. I don't know, I think it's easier because then you know where everything is going over here. This all stays where it needs to. Okay, so that is where we need to be. Now, I am really interested to see what kind of gobbledygook we're going to get on the screen when I first plug this in. I have not erased the previous week's example, so we're going to give this a little power and see what appears on the screen. We did not have anything in our previous example using either of the analog pins, which are these 2 on this side of the board. So I would anticipate we're probably going to see the backlight come on, but with no previous data in the last week's example, I don't anticipate seeing anything here, but we're going to see what happens. We'll plug it in and see what happens. Boop. Nothing. It's a big fat nothing. Interesting. Okay. At a minimum, I thought at least the backlight would have come on. Let me check to make sure I actually plug that in the right place. PCC is there. Ground to ground. Everything looks correct. All right, well, fair enough. Not every component has to do something on power on. It's just, I have to admit, I'm a little surprised that it does absolutely nothing. Yeah, all right. All right, well, I mean, easy enough. If I have a wiring mistake here, we're going to find out when I push the code that's actually for this project. But for the time being, that is it. I'm curious to see if we're going to have any control on the backlight to see how bright this can be, or even if it has a backlight. I would imagine it probably does, but naturally, we're going to find out once we get some programming into it. So, with that in mind, let us get day 21 rolling. So we're going to get ourselves fired up here. Okay, so I did not go get the library yet, so we gotta go do that. So let's go grab that, which I think I could just scroll to the bottom here. Yep, that's what I thought. Alright, cool. Alright, so we got that. And then we're gonna go to import our friend here. What's other tools? She said it, I already forgot. Actually, I think I could just click on the library thing. Maybe not. Let's see here. Ah, there it is. Include library and add zip. Where do I find it? Okay, so we threw that in downloads. We don't even have to extract it. We just need to make sure we include it. Otherwise, we won't be able to do anything with that display. Okay, now that the library is installed, we are not much closer to causing some mayhem. Always a good time. Okay. Alright, now we're going to pick this apart. Alright, let's see what we got here. So it says for safe liftoff, we're going to need to see and react to more information than can be displayed by our 4-digit display or with an LED. Right. So luckily our repair kit contains the little display. The display has 8,128 tiny LEDs arranged in 64 rows of 128 pixels each. Now, as I'm sure you've noticed, we do not have 8,128 pins on the hero board. But we never fear, Explorer. People back in the 2020s were pretty clever and came up with a solution. I like that. Instead of having one pin for every LED, the hero will use 2 pins to send and receive the data, an OLED display, and will instruct the display which pixels to light up using a special language or protocol. Named the I2C. I squared C. Weird. The hero board uses pins 5 and 4 for the I2C communications, so we will wire those 2 pins to our display along with power and ground, giving us a 4-wire connection for displaying messages or pictures on our new display. Cool. I wonder if we're going to end up doing a picture then in a later exercise. Yeah, I imagine we're probably going to be up to something. Let's see here. I love playing with the new component. Always fun. Alright, so computer character fonts, graphical libraries for monochrome displays, logical operands. Right, playing with buffers. Okay. Alright, so like every other exercise, we're going to start with the thing that we do in all of them is include the library so that we can actually work with the hardware we have in front of us. So we're going to include the Arduino library, and then let's get off to what we need to do here. All right. Day 21 lesson. We'll use the library to display messages, which I already installed, but we do need to include it. Installing it makes it available to the compiler, and then including it actually tells the program, hey, I'm about to use this thing I have installed. You can always install additional libraries into your project and never use them, but that's just additional bloat that you don't really need to add if you're not going to actually use it. Nor here nor there. Okay, so the U8G2 library supports many different types of displays. It does this by having a different constructor, quote unquote, for each. A constructor is used to create the handle that we use to access the library code. In this case, our handle will be named LenderDisplay. The documentation for this library lists all the displays supported along with the corresponding constructors and options. This constructor is for our SH1106 128 by 64 pixel generic display. The _F_ indicates that we will use a full-size graphics buffer in the clear buffer send buffer methods to update the entire display at once. The HW_I2C indicates that we will be using the I2C communications with this display. Okay, let's dissect that for a minute. We're working with a generic display that has many individual LEDs, and without some kind of communication protocol that both the display and the board both understand, we would never be able to make the display do what we want, right? This is very similar to installing drivers on your computer to use a particular piece of hardware, right? say you have a printer, right? And you can print to it, and it's got a built-in scanner, but you can't scan to it, right? So if the driver that explains to the computer how to operate the scanner, then it's unavailable. Or you might have the potential that you have a generic scanner driver that allows you to use, like, say, the flatbed glass, but it doesn't work the feeder, right? Having the specific driver to the piece of hardware that you need to use unlocks all the features. Let me display this one more time in a slightly different sense, because this overlaps with the idea of a driver, right? My favorite example with this has got to be the bus driver situation, right? Say that you have a public transportation bus. You get on, you expect there to be a bus driver, right? Now, if the normal driver that operates that piece of machinery is there every day, he's the proprietary driver, right? He's the one who came with the bus, right? He rolled up and he's like, get on in, right? And that driver knows how to work the air conditioning, knows how to operate the radio. If there's something that goes on with traffic, they know where the hazard lights are, right? Say that driver is out sick. And then you have a generic driver, right? A fill-in staff, right? That fills the driving seat of that piece of hardware, right? Well, the generic driver probably could figure out, right, with the knowledge that it has, if it was coded well, right, or they were trained well in this example, how to drive the bus, how to operate the turn signals. But say that this driver doesn't know how to operate the air conditioning or potentially use the radio. That doesn't prevent the bus from moving, but those are features that you no longer have access to because the driver behind the wheel doesn't understand how to operate those things. They're still there in the hardware, but if your software or the piece of software that connects your software, known as the driver, to the hardware, well, then those functions or those features are now inaccessible to you, right? How does that relate to this topic that we're on right now? This display is generic, which allows it to work with a lot of different libraries. We've been given a specific library because this is a guided example. That does not mean that we could not use this display with a different library, right? Since the display itself is generic, there's likely other code that's been written that could potentially be better, more complicated, or of the like, that would also be usable with this hardware, right? We, with this example, had settled on the I2C protocol, right? Which requires us to use analog pins 4 and 5 on our board, right? If there are other protocols that can also control that display, we might end up using different pins on our board. This all ties down to the idea of what's in documentation and understanding what's available to us, and then more importantly, taking those two pieces and coupling them together that you understand and the board understands, so then everybody gets what they want. You make the board do what it wants, the board understands what you're asking it to do, and then you're off to the races. That concept of hardware handling comes up a lot in electronics. The most important thing is that if you can't get a piece of hardware to do what you want, all the pieces of software along the way, from you clicking on a button to the code that's low level that actually interacts with the physical hardware, has to understand what you're controlling and presenting a method for you to be able to use it. Because if the driver has the capability to turn on the radio in our bus example, but there's no mechanism for you to ask the bus driver to turn on the radio, well then congratulations, your driver can do it. But if you have no mechanism to tell them, that is now inaccessible to you. Enough of my rant. But that I find to be probably the best example of hardware to software relationship. You're probably going to hear that again from me again in the future as we toy with additional hardware. But as it goes right now, we've included our library. And then the next thing we're going to do is create our object. This object indicates that we are using this specific display with this specific layout using this specific protocol. The name of our object that we're going to refer to in the code when we want to use the display is the phrase lander_display. Anytime we want to interact with the display and make something appear on it, that's the code we're gonna call on. That's the word we'll use. And then the rest of this is some initialization code. UHE2, I wonder if that's part of the protocol. Reset, and then there's a pin status. Obviously this kind of stuff is documented, and since it was included, that must mean that it was required for us to use the display. But that's why we have a guided example, right? So that we can reuse this moving forward. Okay. All right, so like any good example that uses the serial terminal, we're going to need to tell the code we're going to do it. So inside of our void setup, we're going to start our connection to the serial, right? That's the USB connection we have to the computer. We're going to delay 1000 milliseconds to give the serial connection an opportunity to open, and then we're going to keep going. And then that's right there where we initialize it. So we begin it, we delay, and then we keep going. Okay, and then let's see what we got next here. All right, it says select a font to use for character display. The library supports hundreds of different fonts, which can be found at the GitHub listed below. And then we're going to toy with it. I'll comment the next line if your display shows the text upside down. Interesting. Okay. If the text is upside down, then that would likely mean we have the display upside down, but that gives us the opportunity to rotate that. That's fascinating. I'm going to bring that over, and we'll just leave it commented out. It's not unheard of to hear of software ways of flipping stuff upside down. You do it all the time, especially with like a projector. Projectors are a perfect example of when you software flip something. Projectors have feet, right? And you set it on the feet, right? And that works for when it's on a desk. But say that you want to ceiling mount the projector. Well, the mounting holes are on the bottom where the feet are, which means you're going to take your whole projector, rotate it upside down, and then the feet are going to be facing the ceiling, which means that your picture is now upside down. So then in the software, you just take the remote control, tell it it's wall mounted, and then it goes, okay, whoop, and it flips the picture upside down. So then it's right side up again. Unless you want to stand on your head. But it's cool to see that we have that as an option here. And by the way, I plugged it into the board. I don't know if it's upside down. That part we'll find out. And that's where we rotate. Now, do we have... No, we just simply said... It's commented out, right? So that means this isn't going to run right now. Set display rotation. And there's that UHE2 again, _R2. I don't know. This stuff definitely means something, but other than that, I don't know. We're just gonna keep rolling here. Let's make sure I didn't accidentally copy over something I shouldn't have. Yeah, we're thinking about it. Yep, no, that's fine. All right, cool. Okay, so now we're getting into the main loop. This is the stuff that's going to continue to cycle as we wander through the code. Alright, so it says save the number of vertical pixels required for the tallest character in the current font. This is used later to properly position text on the display. All right, so we're gonna do that. And then we're also going to clear the display, which makes sense, right? So ladder display, clear buffer, clear the internal memory. Okay. All right, so even though we will only be displaying text in this lesson, our display is a graphics display. Text can be displayed at any point on the display, so the library has a set cursor function to locate the first character to be displayed. By default, the cursor's position is set to the bit at the lower left of the first character. But here we set this to be the upper left of the first character, which makes it easier to position our first line of text on top of our display. I'm just going to trust the process on that. This is naturally something that I feel like I would have to toy with a decent amount before I would fully understand that myself. Okay, so it says the title line of our display, draw center string, 0. I wonder if it's a position character. Can you? Oh, that's right. I gotta copy it over to the. Gotta copy that to the terminal before I'll see the hints or the tooltips rather. All right, show me your wisdom. No, you're not gonna see that one, didn't it? Weird. Normally I get the little flyout tooltip when I'm clicking on these things. Alright, well, we'll just keep going then. Alright, display our hello world message on line 2. Moving down front height bits. So, or excuse me, font height. So that means that we don't accidentally draw over top of the previous line of text. Right, so that's going to center it on the display, and then it's going to draw below it without flattening over top of it. Okay, we will blink a message centered in the remainder of the display. However, with this display, we cannot clear just part of the display. The entire display is copied from the buffer every time we call send buffer. So the easiest way to cause some text to blink is to simply add it to the display every other time through our loop and set the delay at the end of the loop to the on-off time. To do this, we will set a static variable which keeps its value between loop executions and only write this message when the variable is true. Then at the end of the loop, we will toggle the variable to the opposite value. Okay. All right, that's definitely not the way I thought we would have been doing that, but sure. Why not? So there's where we're going to declare our variable. It's a static boolean and it's set to true. And then we're going to copy ourselves an if statement. I'm going to go ahead and nab this. I think that was the bottom of that if statement. Make sure I grab the right. Nope. Nope, I made something mad. Oh, we didn't. That's right. I didn't write the. Yeah. I'm calling on a function we didn't declare yet. That's a really common error, which is fine. We'll just keep on going. I'm not worried about that. That error will clear itself as we get to the bottom. Alright, so now we're going to do some wizardry here. Alright, so if blink on, which means that if true, which in this case, it's set to true, which means right out of the gate, it will run through this. Let's center our starting message in the remaining space. To do this, we'll take the height of our display, subtract the height of our title lines, and divide by 2. We'll then instruct the library to center the text vertically from our starting Y position. All right, so we're declaring the variable called centered underscore Y. Our font height is going to be multiplied by 2. And then we're going to add the entire height of the display, subtract the height of the font, multiply that by 2 and divide by 2. Which, yeah, it's just going to do a kind of basic math calculation. This statement instructs the graphics library that the Y coordinate used to position the text will be halfway between the top and bottom of the text. So we're going to call on the display, set the font position, draw the text with a centered Y coordinate. And then we're going to give it the position and say the words stand by. Now, to get onto the blinking portion. A Boolean value can be changed between its two states by setting it to the opposite state using the logical not. Not true is false, not false is true. This would be read as blink on equals not blink on. Right. So blink on is equal to the opposite of the current state, which would make it false. That's what we'll just change it. This is one of those times that it helps greatly to have those comments on the code. Just for legibility's sake, I'm not copying them over in this example, but or in usually most of my examples, just because we're reading through them, we're working through them. Yeah, that's bonkers. So that's just going to switch the state by setting this equal to the opposite of what it is, which is fine. That just flips it back and forth. That's actually a really slick way to do that. All right, nothing is displayed on our display until the buffer is set to the display below. Right, so we're gonna need to actually send our message to the display, to which then we'll see it, and then we're gonna delay by 500 milliseconds to get that blinking effect. Because if the loop just kept going at full speed, we likely wouldn't see the blink effect because the code would be executing too fast. Because we are indicating for the variable of the blink state to be on and off, to cycle back and forth between loops. But if the loop doesn't have a brief pause, we're not going to actually see the blink. This should allow us to actually see this reasonably. All right, so use the draw string method to draw the current string centered in the current display. And this is our function that we need to bring over. And this goes outside of the main loop, so that's going to live down here. We'll verify that, which should clear that error now that I had earlier. Yep, because now the code's there. All right, let me go ahead and save that. Okay, so when we call on our function that's called draw centered string, we accept the position of the Y coordinate from the code further up, and then the actual string that we want to play with. Char. This is a weird way to declare this. The parameter is a string, but the type is a char. I wonder why that is. And then let's see here, byte centered underscore X is the lander. So we're going to take the display's width and subtract the width divided by 2. So we're going to get the X position by just taking the whole size of the display and basically cutting it in half to find the center. And then lander display dot draw str, which is going to tell me instance draw. I would think this is actually going to be what writes to the display's buffer, and then when we send to buffer, so this is going to write it into memory into the position where we want it to appear on the display, and then we choose the method to shoot it over, and it pops it over to the display, if I'm reading that correctly. So I'm believing that's actually about everything that we need to make the display function, assuming I plugged in everything where it belongs. So without further ado, let's see what we get on our display. Wow, it worked. Yes, it colored me surprised because I didn't think it was going to. Now, remember how it said in the code that you can flip it? I currently have us upside down because I plugged the board in upside down. So let me uncomment that line of code from earlier. To flip us right side up. Cool. Very cool. Exploration lander, hello world. It works. I have to admit, I didn't think it was going to. I thought for certain I had something plugged in correctly when the backlight didn't come on. That's fascinating. All right. I have a couple other things I want to experiment here while we're in this frame of mind, right? So we have our font for our lander here, right? And that is our, I'll get the wires out of the way. Oh, did I knock something loose? We stopped blinking. Hit the reset button. Boop. There we go. I didn't see anything in the code that would indicate this to stop blinking at some point. Yeah. Alright. Then here's a question. That data line, well, look at that, so it stops at some point. That's so weird. Let's take a look at that code again. Oh, there it goes. It picked back up again. It's blinking again. That's so weird. I don't know why it's actually indicating to stop doing that. Here, let me see if I can actually zoom this in further so I can keep us down here. All right, so get you about middle of the frame. And yeah, that's all the way up. Okay. Let me see. I will use a box of tissues to prop this up. I want this to be a little higher so that when we see, there we go. Okay. I want to see when I reset the board, right? That, interestingly enough, would explain why I didn't see a backlight, because it doesn't look like it's backlit. Looks like the display itself is just, yeah, like it said, a bunch of individual little LEDs. So that makes a lot of sense. So let me see here. So now if I clear it, right, unplug it and plug it back in. Interestingly enough, that picked up right where it left off. All right, let me unplug that again. Let me give this a minute to like reset. I gotta admit, that's pretty fast to reinitialize the display from power off. Very interesting. Oh yes, you're looking at an OLED display. So this little display is hooked up with power, ground, the clock pin, and the serial pin, which allows it to actually show the super cool stuff we're seeing on the display. So yeah, that's pretty cool. That actually pretty much concludes the remainder of this exercise, which is nifty. So I'm anticipating what we're gonna see for the next go around on the 30 Days in Space franchise here is us working with some variables and sending stuff to the display using some logic like we have with a lot of the other components, which is pretty cool. So yeah, with that, I'm going to wish you all a fantastic evening. I'm planning on being live again next Wednesday, as long as everything works out. And with that, I bid you all a farewell. Bye-bye.